Hi everybody, today we're going to be talking about motion and how to describe an object's motion. So our objectives for this lesson are to differentiate among position, distance, and displacement, something we've been doing in class already, where position is the location of an object with respect to a reference. Distance is when the object changes its position. It's the measure of the length of the path that the object takes in order to change its position, and it's a scalar. Displacement is the straight line length between the final position and the initial position of the object, and it is a vector, so it includes direction. We want to be able to differentiate between speed and velocity, just like when we started talking about distance and displacement in class, and we said that their difference in definition is subtle when we're in physics class. The same is true about speed and velocity. Even though we may use them interchangeably in our real world discussions, in physics class they do have different meanings. And we also want to be able to solve problems involving distance, displacement, speed, and velocity. When we start talking about motion, we want to also make sure that we understand that the branch of physics that deals with motion is called mechanics. So we will spend a good half of the year just dealing in what we call mechanics. When we talk about the motion of relatively large objects, those real-world objects that we can see and touch in our world, people, cars, airplanes, boats, bikes, dogs, even planets, we're talking classical mechanics. We owe a lot of our knowledge of classical mechanics to Isaac Newton, so as a result, some people refer to classical mechanics as Newtonian mechanics. As we come into the 20th century, we start to understand more about the atom. So there's also a branch of mechanics called quantum mechanics that deals with the motion of microscopic particles, those subatomic particles in atoms. We will not be dealing with quantum mechanics in this section. We'll only be dealing with classical mechanics. Now, classical mechanics can be divided into two categories of study. The first is kinematics, where you describe the motion of the object, not taking into consideration what caused the object's motion. We use numbers, we use words, we use equations and formulas, we use graphs, we use pictures, we use diagrams to explain the motion of the object. Once we're comfortable with kinematics, we'll move into dynamics, which is where we determine how forces cause objects to change their motion. Okay, so the first way that we can start representing the motion of an object is with motion diagrams. The motion diagram shows the position of the object at some successive time interval. You must be able to say where and when an object is at a particular position in order to describe its motion. Sometimes keeping track of the object's motion can prove difficult if the object itself is moving differently than just the object. So if you take, for example, this person running down the road, we might disregard the movement of the arms and the legs because they complicate the motion of the person. So a lot of times what we do is we take the object that we're observing and we concentrate on a single point, or we represent it with a single point to sort of show that object just in motion and remove any of the complications of other things that may be moving on the actual object. This is called the particle model. It represents the motion of an object where the object is replaced by a series of single points showing the position of the object at successive times. Right? An object can be in one of two different types of motion, and let's look at how we can figure that out. So let's take, for example, the motion of this bird. Make a particle model diagram of its motion. We're going to represent the bird as a dot. Now remember, the bird's wings, the bird's beaks, the bird's tail, all moving. So I think probably the best place to put the dot is right in the center of the bird. And we mark the bird's position at successive time intervals. Successive time intervals just means you go from time equals 1 second to 2 seconds to 3 seconds to 4 seconds. All right, your time interval is evenly spaced. If we look at the dots that represent the position of the bird, you'll also see that they are evenly spaced. That means the bird is changing its position constantly with respect to time. It changes its position by the same amount every time interval. That's constant motion. Think about it as cruise control in your car. If, on the other hand, the object, take for example this car, and again I'll represent it with a dot and I'll put it right in the side of the car so I don't have any complications from the wheels moving or anything like that. If I mark the position of the car at successive time intervals and I look and I see that the dots are not evenly spaced, as they are in this diagram, we now say the object is in non-constant motion. It is not changing its position by the same amount over each successive time interval. When we want to talk about the where and the when, meaning where is it right now, what time is it when it's there, we need a coordinate system. And we've already been talking about that coordinate system in class when we've been differentiating between distance and displacement and determining how an object changes its position. The coordinate system is there in order to define that zero or that reference point that you are basing the motion upon. So you want to be able to say, is the object moving away from the reference point in a positive direction and a negative direction? Is it moving north? Is it moving south? You need to be able to define that coordinate system. Once you take that coordinate system and you add it into your particle diagram or your motion diagram, you can see that it can be used to determine position and direction. Once you take the object in motion and replace it with that dot for the particle model, you can see that it really simplifies the description of your motion of your object. If you go from the person here and changing their position at successive time intervals to simply the dot, you can look and you can determine the vector of the displacement, the change in position. You can know the time interval. You can get a lot more information from a nice simplified diagram. As we move further into problems, though, that position change may not be as directly given to you as it has been in some problems that we've been doing up until now, where we say a person moved a certain amount to the east or to the west. It may get to the point that you have to be able to pick your coordinate system so that you can decide on what direction the object is moving from the origin or the point of reference. So it might turn out to be just as simple as saying the positive direction is when the object moves to the right of the origin, or the negative direction, which would be opposite, is when the object moves to the left of the origin. The only thing is, when you pick a coordinate system, you should pick it at the beginning of a problem. You should be consistent with it all the way through the problem until you actually come to your solution, so that you can use that information well in your problem. Now, once we have some of that information, how else can we describe motion? In order to fully describe the motion of an object, you need to know the displacement. We already know how to determine that. And we need to know the time interval over which that displacement occurred. So remember, the difference in the final position and the initial position of an object is called the displacement. It is a vector. So you can see here, I can actually draw it in bold. I don't need my little arrow over top of it. But you might not be familiar with this in the front. That is a delta. It's a Greek letter that represents the change in. We will use it with a lot of variables all year. And it essentially means it's the final value of that variable minus the initial value of that variable. It's the difference in the position for when we're talking about displacement. When we want to continue to describe motion, we also need to know the time interval over which that displacement occurred. So the total time, the total change in time needed to complete the displacement is called the time interval. And again, it has a delta in there, the change in time. Time is going to be represented with the variable letter f, and it just means the final time, what time reference did you have when the object was at its final position, minus the time where you started your observation of motion or when the object was at the initial position. For most of us, and most of the time we do things, that initial time is going to be the time equals 0 seconds when we started observing the motion. So a lot of time our time interval, delta t, will just be equal to the final time because our initial time is 0 seconds. All right, once we start looking at that motion and having that information about the object's position and the time it takes to change its position, we can start looking at a graph. Just like a motion diagram, a graph can convey an awful lot of information about the motion of an object, just like a graph can convey an awful lot of information about the relationship between any two variables. In this case, we're just looking between the relationship between the variables of a position of an object and time. So you want to make sure when we start looking at these graphs that you realize which is your independent variable and which is your dependent variable. Generally, you're going to control the time interval at which you measure the position of the object. So it's going to be the independent variable, and it's going to be graphed on the x-axis. The position is going to be what you're going to observe at those times. So that's going to be the dependent variable and graphed on the y-axis. Once you have the graph of a position versus time of an object, you can use it to define the velocity or the average velocity of an object. The average velocity is defined as the change in position divided by the time over which the change in position occurred. If you look at the graph to the right, you'll see that if I took the slope of the line, that would be the change in y over change in x, which is a position, a length measurement, over a time measurement. And that, if you think about your car, miles per hour, it's a rate at which we change our position. That's velocity. So the slope of a position time graph is the object's average velocity. Now, because it is velocity and it is a vector, it has a direction. So the sign of the slope indicates the direction of the velocity. That means if, for example, here we have a positive slope, this line has a positive slope, actually both of them do, that we have a positive velocity, meaning that the object is changing its position in the positive direction with respect to time. You can also have a negative velocity. Negative velocity just means that the object is changing its position in the negative direction with respect to time. Think about your car going forward and backwards. In both instances, you are moving, but you may take forward as being the positive direction. So when you go in the forward direction, you move and change your position in the positive direction with respect to time. You would have positive velocity. If you were going backwards in reverse, you would be changing your position in the negative direction, or your velocity would be negative with respect to time. Right, the magnitude of the slope, magnitude meaning size or the absolute value, is the indication of the speed, how fast the object is actually moving. Speed is a scalar, not a vector, so it just has a size. It doesn't have anything to do with direction. So if it helps to remember, velocity begins with V, it is a vector. All right, speed begins with S, it is a scalar. So you want to make sure that you can differentiate between the two. Remember I said when you're talking about driving in your car, there's a difference between a velocity, which is saying you're driving at 45 miles an hour towards school, and a speed that you're driving 45 miles an hour. But you don't know, are you driving to school or are you driving from school? Okay, so there is a difference between the two. When you're talking about speed, a steeper slope indicates a faster speed. A shallow slope indicates a slower speed because it's the size of the velocity. And if the slope of the line gives us the velocity, the size of that slope would tell us the speed. Remember though, the speed's not concerned with direction. So a steep negative slope would be traveling or indicating a faster speed than a shallow positive slope. The negative and the positive just indicates the direction of the velocity. It has nothing to do with how fast you're going. And last but not least is if we want to try and represent our velocity with equations. So our average velocity, it's defined as the change in position divided by the time interval over which the change occurred. So a couple of things you might want to notice here about how the equation is written. First of all, velocity is a vector. So our V is boldened, or in my case we'll have an arrow on top of it. This little bar on the top means average. All right, it's that overall change in position divided by the time interval. Average velocity doesn't tell us about what happened during the period of motion. All right, during that time of motion, the object could have, the speed or the velocity could have remained the same, could have increased, it could have decreased. Again, think about you driving to or from school. You stop at stoplights, you stop at stop signs, you may change your speed based on the traffic in front of you. All of those things go into an average velocity, meaning how far you went in a particular direction divided by the time interval. When you talk about instantaneous velocity, that tells you the speed and direction at any one instant during your motion. So again, you're driving to school, you look down at your speedometer. Your speedometer tells you how fast you're going at that instant. So it tells us a lot of information about a particular instant in time, but it doesn't tell us anything about the average velocity of the motion. So a lot of different things that we have to look about, and a lot of different terms we have to worry about when we're talking about motion. If we want to change our equation around to figure out the object's change in position as they move, you can use that average velocity. And just by rearranging the equation up here, if you look at delta t, if we again said our initial time is at 0 seconds, the instant we start observing motion is our 0 reference for time. Our final time becomes our delta t, and it just becomes the time interval, the amount of time it took to change your position. If you rearrange this equation a little bit, that's where you can see. You would eventually get that this guy equals, right, v equals df minus di, all right, over t, because our ti is 0. And if we do some rearranging, right, we get v times t equals df minus di. And if we bring our di over to the other side of the equation, we end up with this. So it's just telling us that our position at any one time can be determined by taking that average velocity multiplied by the time and adding into that our initial position. And a lot of times too, what we're going to have is that we're going to take that initial position to be at a 0 point also. So you'll find that that also drops out of our equation quite a bit. Okay, so we will start in class talking about velocity and speed and making sure that you realize that they are different. Fortunately for us, when we first start talking about motion, we're going to talk about objects that move only in a straight line, either a horizontal line or a vertical line. And as a result, you may have noticed when we talk about objects when they change their position in a line, their distance and their displacement are the same. Just that the distance doesn't include the direction value, but the size of them are the same. So when we start approaching problems, that's the first type of motion that we're going to look at. And it does take quite a complication out.